We've just worked through this example. Now, the story here about reagents and testing them for being defective and so on, this is something I made up. The numbers in this example actually come from something completely different. So let me tell you the full story. Okay, so the parameters in the example come from breast cancer screening mammography tests in the 1970s, at the state of screening in those days. And there was a statement prepared, which is this one here. And if you read it, you'll see that it has the same set of numbers in it as the example we've just worked through. So the probability of breast cancer is 1% for a woman at age 40 who participates in routine screening. If a woman has breast cancer, the probability is 80% that she'll get a positive mammography. If she doesn't have breast cancer, the probability is 9.6% that she will also get a positive mammography. A woman in this age group has a positive mammography in a routine screening. What is the probability that she actually has breast cancer? Now, this example was used in a scientific study to see how good doctors and medical students were at interpreting the results of these kinds of tests. Not specifically mammography tests. There are many diagnostic tests that are used in everyday medicine and in specialized medicine as well. And this kind of data is generally available for them. They don't get approved to be used as tests if the data is not available. Now, in the studies that were done in the 70s and the early 80s, up to 95% of doctors and medical students, including from prestigious universities like Harvard, estimated the answer to this question to be somewhere between 70% and 80%, and not 7.76%, which is the correct answer. Okay, now that's a pretty terrible thing, because it meant that if a woman got a positive result and went to see a doctor who didn't understand how to interpret these tests, she could go away thinking that there was an 80% chance that she had breast cancer. Now that would be corrected after a time with a biopsy and so on, but still it would frighten the living daylights out of you if you were told that. So that was the kind of research that was an important motivator for evidence-based medicine, was to try and deal with this kind of problem. Now, I'm going to give you a different explanation of the answer. So we've done a calculation using Bayes' theorem, and I think in the scheme of things it's not really a terribly difficult calculation to do once you know what's involved. But there is a way of thinking about it that's worth knowing as well. This is called the natural frequency method. And I think quite a lot of people find this easier to understand, particularly if you're trying to explain this. If you were trying to explain what's going on to a patient, for example, if you were a doctor, the natural frequency way is a better way of doing it. So you imagine that you have 100,000 batches of reagent, and that 1% of them, 1,000, are defective. Then of the 1,000 that are defective, the test will identify 80%. So 80% of 1,000 is 800. Then there's 99,000 that are not defective, but the test will identify 9,504 of those, that's 9.6%, as defective. And so you can see what's happening here is the false positives, 9,504, are greatly outweighing the true positives. So out of 100,000 batches, the test will identify a total of 800 plus 9,504 as defective. And then we can work out the proportion of those who are identified as being defective that actually are defective. So that's the 800 here divided by the total, which were flagged defective by the test. So 800 over 10,304, and that's where our 7.76% comes from. Let me make a few comments here about likelihood ratio and research study designs. So you've seen this a couple of times now in tutorials. So this is this table where I have a kind of ranking of research designs with meta-analyses of randomized controlled trials at the top and poor old theoretical papers at the bottom. And somebody, not me, has come up with typical likelihood ratios for these different types of research study design. So they range from 19 for randomized controlled trials down to 1.2 for theoretical papers. And then I've done a calculation, which is if you started out, you didn't know one way or the other, so your prior probability was 50%, how big an effect would these different types of study have on your belief, and what would your posterior probability be? So for the randomized control, the meta-analyses of randomized controlled trials, for example, you would go from not knowing to 95% probability that whatever the thing being studied was true, whatever the hypothesis was. And then I've also put in the qualitative description based on that table I showed you a little earlier in the previous video. And then I did another calculation, which was the number of these studies you would have to get to accumulate to a likelihood ratio of 19. Okay, so you can see if you look here at a meta-analysis of cross-sectional studies, which is up at the high end of what you're going to get in management. You would need basically 2 meta-analyses supporting the same conclusions and based on different research papers to get you up to this, a 95% level of belief. But you'll see that a single randomized control, you need 1.3 of those. Okay, so that's about likelihood ratios and research study designs, and we've looked at how you use them to aggregate evidence in the tutorial last week. So if you haven't seen the video of that, I suggest you have a look at it, because it'll be useful for your critically appraised topic. I then want to just point out that Bayesian updating is it's a non-linear thing. Okay, the effect that likelihood ratios have on your moving from your prior probability to posterior probability of belief is not a linear relationship in general. So I've prepared some charts here. So the first one here shows you a likelihood ratio of 1.0. So a likelihood ratio of 1.0 means the probability of the evidence, if the hypothesis was true, is the same as the probability of the evidence if the hypothesis was false. In that case, the evidence has no effect on your belief. So if you look at this chart, in each chart I put a little marker at the 50% probability point. So if you started with 50% probability, you would end up with 50% probability. The evidence would have no effect. The next one, I show a likelihood ratio of 3.2. So this is the boundary between barely worth a mention and substantial evidence, I think it's described as. Yep. So here, if you start with 50 and you take that up, that will bring you across to, I don't know, about 70% posterior probability. Okay, that's a reasonable effect. If you start with a 20% belief, in other words, you think it's more likely that the hypothesis is false than true, that will take you up to about 40%. You're still not convinced, but you've moved quite a way. Okay, by the time you get to say 40% prior, that evidence is going to take you to 60%. So, but at that point, you start to, have some faith in the hypothesis. Then we get up to what they call strong. This is a likelihood ratio of 10, so this is the boundary between substantial and strong. And now you see, if you start with 50, this pulls you up to about close to 90%. Okay, this is very non-linear. Okay, it pulls you up very, very rapidly, particularly if your prior probability of belief is, from about 30 or above. And then this is a likelihood ratio of 100, so that's the boundary between strong and decisive. And really, that sort of likelihood ratio would take just about everyone very close to 100. You'd really have to be starting off with pretty much close to zero. If your prior belief is zero, it's not going to take you anywhere. But even if your prior belief was 5%, this is probably going to take you pretty close to 50%. And if it was 10%, it's going to take you way up the top. And then I won't go through them now, but I've done the same thing at the effective likelihood ratios that are less than 1. Okay. The point I want to make here, I don't expect you to, interpret charts like this. I'm not going to test you on them. The key idea, though, that I do want you to take away is that this is non-linear. Okay, and we are not generally used to thinking in non-linear terms about evidence and probabilities, and that's why it's so important to be aware of Bayes' theorem. There's no getting away from Bayes' theorem. It's just a mathematical truth. Okay, and it's a fundamental, a founding pillar of the scientific method. Okay, so you can't get away from it. It's also useful. I think it's useful to get into the habit of thinking about likelihood ratios. Okay, when somebody, claims to have evidence about something, ask yourself, what's their hypothesis? What are they claiming? What's the probability of the evidence that they're putting forward if the hypothesis is true compared to the probability of the evidence if the hypothesis is false? And what you start to realize after a while, among many things, is lots of stuff that you're going to hear from, say, influencers on Instagram or YouTube or whatever, the probability of, the likelihood ratios are going to be, 1 or less than 1 when you really think about it. And what tends to happen with people that are, one of the things to people that tend to fall for conspiracy theories and, quack medicine and so on, is they leap on the probability of evidence if a hypothesis is true, but they never think about the probability of the evidence if the hypothesis is false. Okay, that's a fundamental problem that they have. So have a look at the charts, but I think the main thing I want you to take away from this is, to remember that this is non-linear. So that little table here, where did I go? Where did I put it? Yeah, this one. So this is, I just keep that handy, okay? Just gives you a reasonable sort of guide. Okay, so that's all for this recording. I'll get on to the next one shortly.